ओके, लेट मी नो रिकॉर्डिंग स्टार्ट हो गई है या ठीक है। Okay, so I was starting with defining momentum, right? Now, Sir Isaac Newton himself, he defined momentum, well, he called it quantity of motion, and he said that it's a measure of the motion that arises from the velocity and the quantity of matter conjointly. Now, quantity of matter is what we call mass. So let me write down this, well, it's a physical law. Let me write down the first one that says that F is equal to, is there a lag, or are you guys experiencing lag as well?
It's fine at my side.
Okay. Because I'm experiencing a bit of lag. But anyways, it says that F is equal to the time rate of change of momentum. Right. So that is, the force is equal to the time rate of change of momentum. And here I would like to emphasize that in any physical law, what is necessary is to understand what each symbol represents in this physical law. So now, well, it does not mean that you might go like, oh yes, I see P here, a vector P, and that's just mass in motion times the velocity. But instead, what I mean is you have to actually physically understand what P stands for. That is, you have to know that P is just not the momentum, but it is actually the momentum of something, right? Say, for example, of a particle of mass m that is moving with some velocity v. And F, of course, is the total force, that is the vector sum of all of the forces that could be acting on that particular particle, right? Now, again, knowing this is actually very important, because only then you can have an understanding of what equations like these are telling you. So, well, let's move on, and let me give you another physical law, and it's called the conservation of momentum. And the conservation laws are actually very important in physics, and you will see that soon. So it states that the sum over all the particles of Pf, where Pf is your final momentum, is equal to the sum over all the particles Pi, right? Now, what does this say? This tells you that the total momentum is a constant in any kind of situation. So, well, again, let's try to understand what this means, and physically, right? So, for example, you take a collision of two particles and say that the sum of the momentum of all of the particles, or if you're taking two particles, well, you'd have two particles before this collision, is the same as the sum of the momentum of these particles after the collision happens, right? By the way, I am experiencing lag on my screen when I'm writing. Are you guys also experiencing that? Or is it, or you can see what
Yeah, a
I
little
wrote?
bit.
There is
Yeah,
lag
we
for
can see,
you
but
as well?
there's a bit of lag.
Okay, I quite don't understand why is it happening.
It's all right, Basil, continue.
Okay, well, okay, so now because of this conservation of momentum, it implies that you can even create new particles and destroy old ones, but it's still true that the vector sum of the total momentum of everything before and after will remain the same. Okay, let's move on to the law of conservation of energy, and that is the same as writing the sum over all the particles of your final energy is equal to sum over all the particles of initial energy, right? So, well, you can say something like that is the sum of the energies of the particles before a collision is equal to the sum of the energies of all of the particles after the collision happens. Okay, now let me write down an equation that all of you probably know or at least have heard of, and that's F is equal to ma, right? But it happens so that this equation is actually a special case of what is a more general expression that we saw well over here, this one, that F is the time rate of change of momentum. And that's because, well, I told you that you can write down momentum as the product of mass and velocity of the particle, right? So now if I say that the mass is a constant, which is not necessarily always true, right? You can have situations where your mass is changing. Well, if I say that it is not changing, it is a constant, then I can just throw this m outside the derivative operator. If I can write this equation well down as F is equal to d over dt of mv. Now, if m is constant, derivative operator would not act on it, and so I can take m outside, and then the time derivative of velocity is just acceleration. And this thing is true for low velocities, because at higher velocities you could have changing mass, right? Now, the law of conservation of energy, if I look at that at low velocities, it will actually become two different laws. Well, firstly, that the mass of each particle is a constant. That is, at low velocities, you can't create or destroy particles, right? And secondly, the sum of the kinetic energies of all of the particles is constant. So that is again to say that the kinetic energy before a collision and after a collision is equal. Now let's very shortly talk about the concept of elastic
Basil, can I ask a
collision.
question?
Yes, sure.
You talked about the changing mass right now. You said that if the velocity is high enough, then the mass can change as time. Like how is it physically possible? Like if I have a block in my hand, then its mass remains same unless I remove something out of it. So even if I'm
Yes.
taking it at very high velocities, why is it that its mass would change? Like would it feel heavier to me then, or what? And why?
Yes, that is actually the consequence of what is called special relativity. And if I start writing down those equations, I would have to do a lot of explaining. But it happens as so that if you take a mass, and if I take a particle of some mass, and if I take it as close to speed of light, the mass happens to change, right? So I hope that answers it. I cannot go into the detail of that, because if I do that, then we would be shifting towards special relativity.
Okay, thank you.
Okay. Okay. So, well, I was about to talk about the concept of elastic collision. Now, think of large objects as particles with low velocities. So say, for example, if you think of a ball as a particle, and then the law that is that the sum of the kinetic energies initially and finally are equal would not be true. Now, you might be thinking why? And the answer to that is because there can be, well, some half mv squared terms, that is the kinetic energies of particles, all mixed up on the inside of the objects. So by inside of the objects, if I'm talking about a ball, it is made up of atoms, and there would be these kinetic energies of these atoms as well in the form of internal motion. For example, you could think of, if you heat up a ball, the kinetic energies will increase, right, of the atoms. So in the collision between large objects, this law actually appears to fail, right? That initially and finally, the kinetic energies would not be the same. So in collision between, again, the large objects, this law will fail, and it is only true for fundamental particles, particles like electrons and so on. You can treat them as, because they are not made up of any more atoms, right? They're fundamental particles. Electron is a fundamental particle. It's not made up of any other atoms or anything else, right? But you see that we still use this law in our calculations, that kinetic energies initially and finally are equal, even when we are calculating, for example, the collision of two balls, right? And that is because we say that it can happen that not much of the energy goes into this internal motion of the atoms, right? We can say that we can make an assumption that the energy that goes into this internal motion of atoms is very small. And so it happens that the conservation of energy appears to be nearly true. And so this is what you actually even call a perfectly elastic collision. Now, I have been talking about collisions, but let's say that if I don't look at a collision, but rather just at the motion of the particle when forces are acting on it, right? Then we get a theorem that simply tells you that the change in kinetic energy of a particle is equal to the work done on this object or a particle by some forces, right? So I can write that down mathematically as delta T, where T is a symbol for kinetic energy, right? Is equal to the work done, right? On it, work done on the particle by forces, right? So now again, your goal here should be to understand what this equation that I just wrote down, what it means, right? So, well, you can say that if a particle is moving on some curve, say it's moving on a path like this, and let's just call it, let's just call this curve S. Now, let's say there are 2 points on this curve, point A and point B. Now, well, the particle is going from point A to point B. That's its destination, right? So it is actually moving under an influence of a force. The particle is moving under influence of a force. And let's call that force, well, let's call it F, right? So for example, if a particle is here, there is some force acting on it in some direction. And let's call that force F. And this is the total force that is acting on the particle. Then if you know this, then if I just tell you what the half mv squared or the kinetic energy of the particle is at this particular point, or let's say at point A and at point B, then they actually differ by the integral from A to B of something that's f dot ds. Now, ds is just an increment of the displacement along this curve that you see over here, that is S, right? By increment about displacement, increment of displacement, I just mean that you take a little portion of this curve and you call it ds, right? So that's your ds. Right. Now, in some scenarios, this integral can be calculated very easily ahead of time. But because that's because the force on the particle depends only on its position in a simple way. But under such circumstances, we can well write that the work done on a particle is equal to the change in a quantity, and that quantity is called the potential energy, or the potential energy of the particle. And such forces are said to be conservative forces. So if a conservative force is acting on this particle, then I can simply write that my change in work done, or the work done, would be equal to the change in the potential energy. Now, here I must say something, that the words we actually use in physics are, well, sometimes terrible. And that's because when I say conservative force, I don't mean that the force is conserved, right? What I'm trying to say is that the forces are such that the energy of the objects that the forces can do work on is conserved, right? So again, it is the energy that is being conserved and not the forces. So sometimes the word conservative forces can be, well, it can be confusing, right? So, well, now let's talk about the total energy for this thing. A total energy for the particle is just the sum of the kinetic energy of this particle and the potential energy. So where T is kinetic energy and V is potential energy. Now, when only conservative forces act, then the particle's total energy will not change, right? Because again, what was a conservative force? It is a force that acts in such a way that the energy of the objects is conserved, right? So if the energy is conserved, then the total energy, the change in total energy should be 0, right? But what happens if non-conservative forces act? Now, these are the forces that are not included in any potential. Then the change in particles energy is equal to the work done on it by these forces, right? So in well, in the case where conservative forces act, I can write that the change in the total energy is equal to 0. And for the case of non-conservative forces, the change in work done, or the change in particles energy, is equal to the work done on this particle by these non-conservative forces, right? So let's talk about something that's very important, in fact, that let me say this, that physics is actually learned by doing examples. So, well, I have told you, or I have at least written down or given you a brief idea about all of the rules that you would be needing for now, right? At least almost all of the rules that you would be needing for now. So now you might say, well, this is very easy. I can just take all of these rules, right? And I can write them down on a piece of paper and just memorize the damn paper, right? Or all of these formulas, right? And then I might know all physics. Well, let me tell you that the only problem with that is it just won't work, right? So what we have to learn is actually, how do I apply the mathematics to physics, right? In order to understand nature, or even in order to understand well, problems that you have to solve, right? Now all these equations, they just keep track of things for us. So we use equations as tools, but of course, to do that, we must know what objects the equations are speaking about. And so I had to tell you what these equations are actually telling you, right? Now, I will be honest with you that I can't simply just transform you from someone who can't analyze new situations. And by new situations, I just mean when you're looking at a problem to solve that problem, and to someone who can, right? And this is why we have to look at problems of applications in the physical world, right? As well, only from these examples you would be able to catch on. Now, well, let me give you an example over here that, well, there was a time in ancient time, there was this thing called the Babylonian mathematics. Now, Babylonians could do a lot, right? They could do a lot of things. and they could even solve quadratic equations, and also had, well, tables for solving cubic equations. But they could never write down an algebraic expression, right? So they did not have the mathematics. They had no way of writing down formulas. So what they did was they did one example after another. And the idea of all of this was that you are supposed to look at examples until you can get the idea. And again, because they did not have the power of mathematics. So the only way that you can understand physics is by following the Babylonian way of doing a whole lot of examples until you get the idea. So this is our motivation to do a lot of examples or problems in physics. Now, some of you might think that physics can be, well, it can be done by simply just plugging in formulae, right? And well, if for example you see a question or a problem, and well, you see that it has some terms like it has mass, it has acceleration, and well, you quickly remember that there is a formula I have, that force is mass times acceleration, and you would just put that formula in this thing, right? But the problem with this is that you might not think about the physics behind the problem. And well, I will actually give you an example where you will see that if you don't look at the physics of the situation and you know the mathematical formulae, even though those formula might seem to fit in that particular situation, you will see that if you don't think about the physics of all this situation, you will not get the correct answer, right? And that's obvious because you have to understand the physics of the situation. So, well, for this was most likely it for today, because now from this point, I would like to give you an example that I just mentioned that will show you that why understanding the physics behind a situation is important. And well, it would take some time for me to do so. So what I would do now is, let me just give you some of the, or let me just tell you some of the problem solving techniques that might be helpful to you. Now, I'm not writing down things on my tab because it appears so that I have some technical difficulties. I'm writing things down and they just appear to lag, and some of these things appear on my page, and well, most of them do not even appear if I'm writing them down. So I'll fix that problem for tomorrow's lecture. But let me just again, let me just give you some useful problem solving techniques, right? So if you read a problem, the first thing that would be very helpful for you to do is you should sketch the problem, right? You should make a sketch of the problem, and it's called a free body diagram. And in that, you indicate all of the forces that are acting on this diagram, or at least you confine your system. And for example, if you're looking at, let's say you're looking at a car that's moving, the only forces that you would need to consider are the force of gravity, the weight of this car, and the driving force of this car. And of course, you would also be considering friction, but you would not be considering forces like the intermolecular forces, right? So in a free body diagram, you indicate forces that are required, you indicate velocities, and so forth, right? And then the next step should be that you write down the given quantities in your expression, in your problem, and you write them down. And then you think of some equations, right? But again, here, just thinking of equations is not going to be very helpful. You have to analyze the whole problem by keeping principles of physics in mind. So that's your strategy. And then you use the algebraic manipulations. like differentiation or integration is usually required. And then finally, you put the actual values and you go ahead and solve the damn problem, right? So this was it for the lecture. We still have 20 minutes to for the lecture to end, but because I'm having these problems in writing, so it would be almost impossible for me to do an example over here. And the next thing I had in mind was to do an example. So we will skip that for tomorrow's lecture.
Okay, thank you.
If you have any questions, I mentioned earlier as well, you could stop me in between and ask me, but I did not really hear any question. So either you understood everything or everything just went over your head.
No,
I hope
actually,
it's
I
not
have
too
a
late.
single request.
Yeah.
Could you please explain the concept of conservative and non-conservative forces tomorrow in some more detail? So maybe an example or two that would help. I
Oh,
think.
sure. Yes, I would love to. Sure, I would do. But I
Okay,
hope
thank
you
you.
still get the idea that a conservative force is a force that acts in a way where the energy of the system is conserved, right? So it's not the force
Right.
that is conserved, but the energy that is conserved. And a non-conservative force would be a force that acts in a way where the energy is not conserved. But of course, I get your point. I will give you an example tomorrow where I'll show you what I mean by this.
Okay.
Yeah.
Okay. Thank you.
Okay. No more questions?
None from my side. Thank you.
Right. Okay. So I guess that's it for today. The physics class is officially over. Zohran, if you're trying to say something, I cannot hear you. Your mic
I
is
was
muted.
saying, Basil, it was a very nice lecture.
Yeah, thank you.
Okay, people, then we'll meet tomorrow. Same time and same place. So, Allah Hafiz.
Okay. Allah Hafiz. Thank you.
Take care. Allah Hafiz.
Allah Hafiz, people.